This is the first in a series of videos in which we'll look at some past CSEC physics questions. In this video, we will focus on questions on atomic or nuclear physics and radioactivity. So the first question that we look at comes from 2019, paper 2, question 6. Now, this question starts off by saying that lithium-7 is an isotope of lithium. The mass number is 7 and the atomic number is 3. 1. Use the information given above to determine the number of protons and neutrons present in an atom of lithium-7. Now, before we go into exactly what the question asks us, let's look at the term isotope, right? Isotope. Now, what is an isotope? Now, isotopes are atoms of the same element having the same number of protons but different number of neutrons, right? So once again, isotopes are atoms of the same element having equal number of protons but different number of neutrons. And of course, in many cases, a lot of atoms actually exist as isotopes, but it's just that some are more common than the other, right? So for instance, carbon is commonly known to have two isotopes, carbon-12 and carbon-14. Carbon-12 is the more stable of the two isotopes, whereas carbon-14 is the radioactive isotope, which of course is used to do carbon dating in trying to determine the age of old things or artifacts, right? So when we speak about an isotope, of course, isotopes of the same element have equal numbers of protons but different number of neutrons. And because they have equal number of protons, it means that they will have equal number of electrons on the shells because they're talking about regular atoms, and of course they will have different mass numbers. So in the case of carbon-12 and carbon-14, 12 represents the mass number, also referred to as the nuclear number, and in the case of carbon-14, the mass number or nuclear number is 14. Now carbon-12 may be written as this using the regular method of representing an element. So the mass number is 12, and of course the proton number, which of course is 6, right? Similarly, carbon-14 may be written like this, C14-6. So see that these two isotopes, they will have the same number of protons, but they have different mass numbers due to the fact that they have different electrons, different number of electrons, right? Now let's go back to the question. Now in this case, the question is talking about lithium-7, so we can represent it as lithium-7 so we have lithium-7, which of course tells us that it has a mass number of 7, a mass number or nuclear number of 7. Well, the question actually went on to tell us that. So that tells us that lithium-7 is an isotope of lithium. The mass number is 7 and the atomic number is 3. So if we want to represent lithium using the regular symbol, we can say that Li73, right? So generally, if we see an element represented like this, X, A, Z. So X would represent the symbol of the element, and of course Z represents the proton number, which of course happens to be the same as the atomic number. And A represents the mass, or what is often referred to as the nuclear number, right? So we represent lithium in that manner. The relationship between A, the mass number, Z, the proton number, and N, the number of neutrons, is this. So we say A is equal to Z plus N. So the mass number or the nuclear number is equal to the number of protons plus the number of neutrons. So in this particular case, we're given the mass number of lithium, we're given the atomic number as well, and they want us to find the number of protons. So therefore, it simply means that in the case of lithium, the number of protons Z is equal to 3, and the number of neutrons N. If we were to simply transpose, then N would be equal to A minus Z. So therefore 7 minus 3, that gives us 4. So therefore what this means is that an atom of lithium-7 will have 3 protons and 4 neutrons, and of course these will be in the nucleus of the atom, right? Now in part 2 of the question, we're basically told to draw a clearly labeled sketch of the structure of the lithium-7 atom. So this is basically a simplified version of the atom. So we know that basically atoms comprise of a centrally dense portion called the nucleus, which consists of the protons and the neutrons. So in the nucleus of lithium-7, we will have 3 protons and 4 neutrons. 4 neutrons, right? And because lithium-7 has 3 protons, it also means that since it is a regular atom, it will have 3 electrons on its shell. So we draw the first shell. Now the first shell can hold a maximum of 2 electrons. We represent the electrons using crosses. So we'll have X, X. So those are the first 2 electrons on the 2 electrons on the first shell. So that leaves the second shell, which will of course will have 1 electron. So we have 1, 2, 3 electrons. Now the question wants us to draw a clearly labeled sketch. So basically, if I talk about the sketch, then this would basically be the nucleus. This would be, or these would be the shells, and these X's represent the electron, right? And therefore, there we have it. This is basically a label diagram of the structure of lithium-7, right? Now, the next part of the question, so 4 marks for that part of the, 2 marks to determine the number of protons and neutrons, and a further 4 marks for drawing the clearly labeled sketch of the structure of lithium-7. Now, the question goes on to part B, which says that in 4 days, in 4 days, the activity of a sample of lithium decreases to 1/16 of its original activity. So in 4 days, the activity of a sample of lithium decreases to 1/16 of its original activity. And they want us to first define the term half-life. Now, let's talk about half-life. The half-life of any radioactive sample is the time taken for the number of atoms or the activity to decrease to half its value. So we can define the half-life of any radioactive material in terms of the time taken for the number of atoms to decrease to half, or the time taken for its activity, which is basically the rate of disintegration, to decrease to half its value, right? So for 2 marks there, half-life, the half-life of any radioactive sample is the time taken for the number of atoms or the activity to decrease to half its value, right? Easy 2 marks there. In part, so that's part B1. In part, where's the next part of it? Oh, right. So going back up, it tells us that in 4 days, the activity of a sample of lithium decreases to 1/16 of its original activity. And they want us to determine the half-life of lithium. So let's represent that in a little table, right? So in 4 days, the activity of a sample of lithium decreases to 1/16 of its original activity. So let's represent this, say time. Let's say time in days, and this is the activity. So time in days, the activity, right? Now, at t equals 0, and we're just choosing a number here for simplicity, right? So at t equals 0, let the activity be equal to 1, right? So what we're told is that after 4 days, the activity has decreased to 1/16 of its original activity, right? So, when we say time in days, really and truly what we should have is basically not time in days, but all right. So let the initial activity be equal to 1, right? So what we're basically going to be doing is looking at the number of half-lives. Let's focus on that first. Number of half-lives. Right, so number of half-lives, and let this be the fraction of the sample remaining. Right? So the fraction of the sample remaining. So we're looking at this way because, as I said before, when we speak about half-life, it is basically time taken for half the sample or half the number of atoms or half the activity to decrease. So what we're basically going to do is we're going to look at how many half-lives it will basically take for 1/16 of the sample to remain, or basically for the activity to decrease to 1/16 of its value. So usually after one half-life we have a half of the sample remaining. Good? After a second half-life, that half is now halved, and so a half of a half, that gives us a quarter. Right? After 3 half-lives, then the previous portion is now halved again, and half of a quarter, that will give us 1/8. After 4 half-lives, then it is halved again, and a half of 1/8, that gives us 1/16. So this basically means that after one half-life, half the sample remains. After 2 half-lives, a quarter remains. After 3 half-lives, 1/8 remains. And after 4 half-lives, 1/16 remains. Now we did this in terms of the fraction of the sample remaining, but it also applies to the activity, or the fraction of the activity of the particular sample, right? So if we're talking about the activity, then basically if the initial activity is, say, 1 for simplicity, after 1 half-life, then activity will be a half. After 2 half-lives, it will be a quarter. After 3 half-lives, it corresponds to 1/8. After 4 half-lives, it corresponds to 1/16. So what we're told is that in 4 days, the activity of the sample decreases to 1/16 of its initial value. So basically what we've seen from this table is that for the fraction remaining to be 1/16, 4 half-lives must elapse, right? So basically 4 half-lives would be equivalent to, in this case, we're told it is 4 days, so that is equal to 4 days. And therefore this means that the half-life T half is equal to 4 days divided by 4, so this gives us 1 day. So therefore it means the half-life for this sample of lithium-7 would be 1 day. Right? So once again, when we speak about half-life, we can speak about the number of atoms. We can also speak about the activity of the radioactive sample, right? And generally, the half-life is the time taken for the number of atoms or the activity to decrease to half its initial value. All right, so moving on to part 2 of that. Well, that was part 2 there to determine the half-life of lithium. So the half-life works out to be 1 day. All right, let's look at part C of the question. Part C of the question says, calculate the energy given off in a nuclear reaction if the change in mass is 0.2014 U. So what they want us to do is to calculate the energy given off in a nuclear reaction if the change in the mass is 0.2014 U. So let's write down the information that we have. So the change in the mass, we can call that M. Some books would have put delta M since it represents a change in the mass, but we'll just use M. So change in mass M is equal to 0.2014 U. Now we're also given that U is equivalent to 1.66 times 10 to the minus 27 kilograms. Right? And of course we know that the speed of light c is equal to 3.0 times 10 to the 8 meters per second. Right? Now whenever you're given the masses of atoms at this level, it is not uncommon to have it expressed in what are called atomic mass units. And the U here is basically representing the atomic mass unit. So one atomic mass unit is essentially equivalent to 1.66 times 10 to the minus 27 kilograms. So therefore, if during the nuclear reaction, the mass changed by this amount, we have to basically express that in terms of kilograms and then use our equation E equals mc squared to calculate the energy that was released during that reaction, or during that during that reaction, right? So it therefore means that 0.2014 U is equal to 0.2014 times 1.66 times 10 to the minus 27 kilograms. And that gives us, we have the answer there. Right, so that is 3.34 times 10 to the minus 28 kilograms. So this is 3.34 times 10 to the minus 28 kilograms, right? This will have quite a few number of decimal places, but we could leave it at, say, 2 decimal places or three significant figures. And then, of course, we use our equation E equals mc squared, Einstein's famous equation, to calculate the energy given off. Now, before I go any further, I must remind you that whenever using this equation, the mass lost, m, must always be in kilograms, right? Because this is calculating energy in joules. And in order to calculate energy in joules, m must be in kilograms, and of course c, or speed of light, in meters per second. In some cases, as in this question, the mass will be given or would have been calculated in atomic mass units. You are then expected to first express that in kilograms before substituting the value into this formula, right? So this now gives us E is equal to 3.34 times 10 to the minus 27, that would be in kilograms, times 3.0 times 10 to the 8th meters per second squared. And that basically gives us three significant figures, 3.01 times 10 to the minus 11 joules, right? So you have to basically be quite proficient at your calculator and know how to deal with operations like these, because at the end of the day, if you make a mistake in entering the values into the calculator, your answer will be incorrect and you lose some marks because of the answer not being what it's supposed to be, right? So there we have it. The energy released in this particular nuclear reaction is 3.01 times 10 to the minus 11 joules. So this was question 6 from May, June 2019, paper 2.